This is Heather Fody and Gabrielle Aguilar reporting on the physics involved in the art of figure skating. At the beginning of the skater's routine, they present their first form of physics through tension and Newton's third law pairs. They balance their weight against each other through their arms releasing tension. Both the male and female skaters exert a tension force equal and opposite to each other.
Through the majority of their routine, the skaters move at a constant velocity by gliding over the ice with relatively no friction. Because of this, there is no acceleration. Furthermore, Newton's first law states that objects that are in motion tend to stay in motion unless acted upon by an unbalanced force. In this case, a skater would apply more force to the ice, creating more friction and unbalancing their horizontal force. The skater would no longer be going at a constant velocity and would slow down.
The moment the male skater holds his partner's waist, he creates potential energy for the upcoming lift. After his partner is tossed and in motion, the energy she possesses is an example of kinetic energy at work.
Speaking of work, the energy the male skater needs to perform the lift requires him to transfer his energy into making his partner's body accelerate.
At the point when the female skater is completely out of contact with her partner, she becomes a projectile. In the air, the only force acting on her is gravity.
Since gravity was the only force acting on her body, Newton's second law says that acceleration equals net force over mass. In this case, gravity was the net force because her mass cancels out, which leaves negative 9.8 meters per second squared as the acceleration.
The next toss is a more significant example of projectiles, because she is thrown in a more parabolic path when in motion. If her angle of trajectory and initial velocity were known, one could use kinematics to solve for the amount of time it would take the skater to reach the ground and the distance she would travel.
Work comes into play here too, Heather! Work is known to equal force times distance. Since the distance she covered in her motion was greater than her first toss and the force the male skater needed to throw her increased, the work required to throw her is larger.
During the single jump, each skater exerts an increased amount of normal force on the ice to accelerate upward. This unbalances their vertical net force, which causes a change in acceleration. This is an example of Newton's second law because the gravity force and normal force no longer cancel each other out.
Good thinking! It also exemplifies kinetic and potential energy. In preparation to jump, the skaters build potential energy while still on the ice. When they push off the ice, however, the potential energy converts to kinetic energy.
In their next move, the male skater lifts and holds his partner while skating. The normal force she exerts on him by her body is equal to the force he exerts on her by his hand. Their normal forces are applied in the opposite direction, hers being negative and his being positive. This is considered another one of Newton's third law pairs.
Towards the end of the performance, both of the skaters perform a camel spin and a sit spin. By making their bodies more compact, the skaters increase the velocity of their spin and accelerate. There would be less air resistance acting against their bodies because they have minimized their body's surface area.
Now let's quickly look back at some of the moves performed earlier. As we said, the only force acting on the female skater while she was in the air would be gravity. Because of this, she would be accelerating downward. If we were to draw a force diagram for her in the air, there would be one vector pointing down vertically to represent gravity. There are no forces in the x direction. We could calculate the force of gravity by multiplying the mass of the object times negative 9.8 newtons per kilogram. If, for example, the skater weighed 50 kilograms, then the force of gravity would equal negative 490 newtons. Also, in one of the moves when the male skater throws his partner in the air, we could use certain equations to solve for the time she was in the air and also the distance she would travel. It would look something like this. First, we solve for our component velocity vectors by using trigonometry. Then we use the vertical displacement equation to solve for time. The displacement equation is displacement equals 1/2 acceleration t squared plus initial velocity times time. After finding time, we could use the same equation for the horizontal displacement, except plugging in t equals 1.8 seconds and solving for the change in x. Finishing off their lovely performance, the skaters have come to a complete stop. This resembles Newton's first law because without applying force to the ice, they would still be moving and not at rest. I'd say this performance was a 10, right, Gabby?
Yes, it was.